Hello, 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 hello. Warm welcome. Thanks for joining us. Grab your notebook, pen or pencil, whatever you want to write with. We're about to enter the void. This is math from the void. Math coming at you out of nowhere. And today we have a problem from the 1992 AP Calculus BC exam. But if you're in an AB level of understanding, you can still totally approach this problem and complete all three parts. So let's get started. We have an interesting function. We have a piecewise function here. You might imagine this. Sometimes you guys draw this sort of thing. And we don't need to know the nitty-gritty about what it looks like, but it's helpful to just notice what pieces there are. This is an upside-down quadratic when x is less than 1. And this is a right-side-up quadratic with some k and p missing when x is greater than 1. So just generally, I'll have this potential breaking point. I say potential because I don't know that it's actually broken, but it's potentially broken. And then what can we do here? So this is going to be something like this. I happen to know that that's where the vertex is also going to be. But we don't know how high up it is, actually. We don't know how high it truly is. So it's, I mean, if you understand quadratic functions pretty well, you'll understand what it is. But, you can think maybe it's, who knows how high up it is, that kind of a thing. I'm just going to leave it right, let's say like right there. I don't know, maybe that's a decent idea. And then this other quadratic is a piece like, that kind of a thing. And we don't know if it's just half of it, right? It would be nice if it were like the smooth part of it. So if the vertex also lined up, that would be really nice, but that's not necessarily true. And we don't even know that this is, perfectly cut in half in the first place. So it's possible that this thing is not even perfectly cut in half. Maybe, for example, maybe there's still has to go down a little more and then goes up. Or maybe it's already on the part where it's going up a lot. There are different portions of this parabola that can be drawn. So we're not really too sure about that, but I'm just going to draw it something like this, which doesn't have the smoothness, but it could potentially connect. Okay. Now let's look at the actual problems. Now that we know what we're even talking about, right? Before I answer the questions, before I read the questions, I want to put my mind in the function, whatever it is that they give me, as much as possible. But quickly, I'm not trying to go too into the nitty-gritty on what exactly the vertices are and stuff. So now let's answer this. For what values of k and p, okay, makes sense, we're looking for these missing values, will f be continuous and differentiable? So let's answer the continuous part first. The continuous part, I can use my pieces here. The continuous part means that they're connected. So I called this a potential breaking point because it's where one piece stops and one piece picks up. But we don't know that they pick up on the same y value. Maybe it does. So this is saying we want it to connect, but we also want it to be smooth, which is very interesting because even without doing any specific calculus, I know that that means they have to have the same slope. And I happened to pretty quickly figure out that the first one has its vertex at x equals 1. That's not as obvious to you maybe, but it's true that it has the vertex there. So we would need to be at the vertex of this other parabola in order for it to be smooth. That's just something useful to know. But realistically, what we would do with any piecewise function is we would make sure that it's continuous by saying f of x has to be the same on both sides. So basically, both pieces need to be equal when x equals whatever that breaking point is, 1. We're going to check the limit as x approaches 1 from the left, and we're going to see that that is equal to the limit as x approaches 1 from the right. And if they're equal, then they're going to the same place, and the left piece happens to be also defined at x equals 1. So that would also tell us f of 1. So let's see what that's going to give us. From the left, that's just going to give us 2 minus 1, which equals 1. On the right, that's going to give us 1 plus k plus p, which doesn't really simplify, so it's just 1 equals 1 plus k plus p. So this means that 0 equals k plus p. Interesting. So k and p are opposites, apparently. But we also want it to be differentiable. So this means we want f prime to be equal. That way it's smooth. The derivative needs to be the same on both sides as well. So we're trying to basically make sure that the limit as x approaches 1 from the left of f prime of x, which is the slope of the function for the left piece as we're getting closer to x equals 1, and that needs to be equal to the limit as x goes to 1 from the right of the derivative as well. So making sure the slopes are equal as they approach 1, which means it's smooth, aka differentiable. So what is the derivative of the first left piece? That's 2 minus 2x. So this is going to be 2 minus 2, because x is 1. So that's 0. And on the right side, we're going to end up with 2x plus k. And since x is 1, that's just 2 plus k. And so now this tells us that k equals negative 2, and that means p equals positive 2. Okay, cool. For the values of k and p that you found, makes sense, on what interval or intervals is f increasing? Now, what do you notice about this function that we drew? It looks like it's increasing literally everywhere except where it's flat at x equals 1. So I can pretty much guarantee you that it's going to be from negative infinity to 1 and from 1 to infinity. Let's see that that's the case. So how do we find intervals of increasing and decreasing? We want to find the zeros, but we want to find them separately for the pieces because we don't want to find zeros for a piece that aren't on its domain. So what I mean is if there were a function that had a flat point on its complete graph, but maybe not on the portion that it's represented in this function, then we would be getting some false zeros. So let's just work with each piece at a time. If we do f prime for the first left piece, if we set them equal to 0, that's going to be 2 minus 2x equals to 0. So 2 equals 2x. So 1 equals x. So that gives us a flat point, which we predicted. I mentioned that that was the location of the vertex. So that's the flat point for this parabola, for this quadratic function. And it's increasing the whole time, leading up to it. If you don't believe me, we can look at the original function. We can look at this function, make a chart. 2 minus 2x. It's going to have opposite behavior than normal. So this is going to be plus, and this is going to be minus. So it's increasing from negative infinity until 1. And then let's look at the other piece. When is that one increasing? Well, the other piece derivative is 2x plus k, which we found out was just 2, right? Oh, negative 2. Okay. So 2x minus 2 equals to 0. Hey, that is also 2x equals 2, and that is also x equals 1. So that means that there's a flat point at 1, again, which we predicted that that's the vertex because it needs to be smooth, vertex on vertex. And let's just follow the behavior of the chart. Of course, this one's going to follow the normal behavior because the coefficient on x is positive. We have negative and then positive. So what do we do with these intervals? Remember, the left piece is only up to this spot, so it's increasing, and the right piece is only up to this spot from the left. It starts at 1, so like I said, everywhere it's increasing. F prime is greater than 0 on the interval from negative infinity to 1, which is where its flat point is at, and then again from 1 to infinity. There we go. So having that sketch, even though it took me, 2-3 minutes to draw this out and consider all those little possibilities about the function, working that into my process, making that a part of my workflow in this problem solving It really contributes to being able to answer questions about things like maximums, minimums, increasing behavior, decreasing behavior. If they ask me about the concavity, well, look, I know exactly what the concavity is now. It's concave down, and then it switches at x equals 1. It becomes concave up. And here we go. Using the values, find the points of inflection. So they want me to look at second derivative because the points of inflection are when f double prime changes sign. Okay? And support your conclusion. So, I mean, if we can show that that happens somewhere, then we've supported our conclusion. So let's take the second derivative of the pieces. So the first piece, -2, that means that the second derivative, if we put that on a chart, we don't need to, it's not going to have a bunch of factors or anything. It's just going to be negative the whole time. It's just -2. It's not -2x. It's just -2. And that's going to happen all the way until we get to x equals 1. And then on the next piece, in fact, I'll kind of draw it like this. Then on the next piece, the second piece, the derivative of that is just +2, because the derivative of 2x minus 2 is just +2. So then it just becomes positive. So since f double prime changes sign here at x equals 1, that means that there's a point of inflection there. And it wants me to find the point of inflection. It doesn't say the x coordinate specifically. It says the point of inflection. So here we go. We're going to plug in 1. And based on the piecewise definition, we're just going to use the left piece, this piece, because it says whenever x is less than or equal to 1, use this piece. And if we plug that in, we just get 2 minus 1, which is 1. And that is your point of inflection. Okay, so this is some great analysis on a piecewise function that involves quadratics, but in a way that just basically asks you about intervals of increasing and decreasing, making you find some of the parameters of the equation itself. All right, hope you learned something from that, and I hope you're keeping up with the pace as you continue to watch these videos, because my pace is slower than it would be if I were just taking the exam. I wouldn't have to explain all of these things. I would just sort of do it. But I hope you understand that this sort of fast, driven, focused pace is exactly what you need to be successful. The knowledge is one thing, but the focus is a very important element of taking this exam. All right, enough lecturing from me. I'll see you next time in the wood.